Hi, and welcome to Math 6 BCPS-TV style. My name is Laura Potter, and I'm your host for today's lesson. Before we start doing math, let me tell you a little bit about me. The 5 humans, 2 dogs, and 1 cat in the picture are my family. The humans and I enjoy playing board games after dinner. You'll get to meet everyone in a few minutes. Our dogs, Maya and Honey, love to play fetch and eat treats. Our cat Sassy can almost always be found laying in the sun or sitting in a box. To start, we're going to warm up our brains with a Think About It task. Today's Think About It asks you to decide which one of the pictures does not belong. Take a few seconds to think about which picture you think does not belong, along with the reason why. Let's hear from my family to learn about their ideas. As you listen, pay attention to the reasons why they selected their particular picture. Hi, Victoria.
Hi.
Which sign do you think doesn't belong?
The speed limit 45.
So letter A?
Yeah.
How come?
Because it says speed limit while all the other ones say maximum. Also, all the other ones end in a 0 while this one ends in a 5.
Oh, cool. Thanks, Victoria.
You're welcome. It's right now.
Hello.
Hi.
Which one do you think doesn't belong?
I think the maximum 100 doesn't belong
Why not?
because it's the only one that's triple digits and the other are only double digits.
Nice. I've never seen a speed limit sign that says 100, maximum 100 miles an hour. Hi, Tim.
Hi, Laura.
Which one do you think doesn't belong?
I think in this case, picture C is different from the others.
Oh.
Well, picture C has units on the sign.
What do you mean the units?
Well, picture C has km/h, and that means kilometers per hour, and that's the units.
Oh, and A, B, and D don't have that on the sign.
Right.
Nice. Thanks, Tim.
You're welcome.
The material covered in this first mini lesson is the same as the material in the print packet for Math 6 during the week of April 20th. This is our first lesson. On the screen is our first learning objective. Today, we will define, write, and graph inequalities that represent real-world situations. Now we're going to move into the Learn About It section, and we're going to learn about inequality symbols. The inequality symbols that we're going to be learning about are in the left-hand column of the table. The first thing that we're going to look at is what those inequality symbols mean. This symbol means is less than. This symbol means is greater than. This symbol means is less than or equal to, and this symbol means is greater than or equal to. You may be familiar with these symbols from previous math courses. There are also some different words and phrases that you might use to represent these inequality symbols. We're going to do some examples in a minute to get you familiar with those word phrases. Finally, we need to know what type of circle to put on a number line if we're representing an inequality statement. If we have a less than or a greater than symbol, we're going to use an open circle. If we have a less than or equal to or a greater than or equal to symbol, we're going to use a closed circle. So here are those examples that I was talking about earlier. The first example says the team has scored fewer than 5 runs in each game. So I think that means the team scored 4 runs or maybe 2 runs or maybe they scored no runs at all. I know that because of the key phrase fewer than. And when I look at my table, I can see that the word phrase fewer than is another way of saying is less than, and I'm going to use this inequality symbol. So the score that the team has made is fewer than or is less than 5 runs. The next example that we're going to look at says no more than 8 people can ride in the elevator. So what that means is that the elevator could be empty, 0 people. 7 people could ride in the elevator. But I also think that 8 people could ride in the elevator, no more than. Yeah, if 8 people are in there, that's okay. And the phrase no more than is what helped me to unpack and understand this problem. When I look at my table and I see the word phrase no more than is another way of saying is less than or equal to. So I'm going to be using this symbol. So the people that can ride in the elevator must be less than or equal to 8. The next problem that we're going to look at says more than 25 students try out for the team each year. So maybe there are 40 students, more than 25, or 30 students try out for the team. The phrase more than is what clues me in that the numbers need to be greater than 25. So more than is up here in the greater than column, or the greater than row, excuse me. So the students that try out for the team needs to be greater than 25. And the last problem says there are at least 75 fans at each home game. So I'm going to think about the Baltimore Orioles and them playing baseball this spring. So there are at least 75 fans at each home game. So there could be 100 fans or 200 fans or 1,000 fans. The phrase at least is what helps me to understand that 100 or 200 or 1,000 are numbers that would make this sentence true. At least is another way of saying is greater than or equal to. So I'm going to use the greater than or equal to symbol. So the fans at each home game is greater than or equal to 75. So now we're going to look at an example where we're asked to graph an inequality statement on a number line. The inequality statement that we're asked to graph is y is less than or equal to -3. And I'm going to follow the 3 steps that are outlined for me on the screen, and you can follow along in your print packet. So the first thing that I'm asked to do is I'm asked to draw a solid circle at -3. So here's my solid circle at -3. And the reason why I'm using a solid circle is because the symbol is less than or equal to, and I can include that value as a solution. Next, it says to shade the number line to the left of the -3 to show that numbers less than 3 are solutions. So I want to think about that for a minute. The numbers that are left of -3 are -4, -6, and all of those are less than -3. So those are all the values that make this inequality statement true. So I'm going to shade to the left. So now my inequality is shown on a number line, and what it's saying is that any number that's on the shaded region is a solution to this inequality. So -9 and 5/10, -6 and 2/3, those are all solutions to this inequality. The last step says check your solution. Choose a number that is on the shaded section of the number line, such as -4. Substitute in -4 for y. So here's -4, that's in the shaded section. I'm going to rewrite my inequality, which says y is less than or equal to -3. And I'm going to substitute or replace y with -4. So -4 is less than or equal to -3. And I'm going to read this statement one more time to myself to make sure that it's a true statement. -4 is less than or equal to -3. That's true. -4 is less than -3. So this tells me that I have correctly graphed this inequality statement on the number line. We're going to skip example 2. I'm going to let you try that one on your own. And we're going to move to example 3, which is an example where we're going to model a real-world situation by using an inequality, and we're going to graph that on the number line. So let's read the situation together. To test the temperature rating of a coat, a scientist keeps the temperature below 5 degrees Celsius. Write and graph an inequality to represent this situation. First, I need to change my pen to blue because -5 degrees Celsius is chilly. So I'm going to think about some possible temperatures that are below 5 degrees Celsius. -4 is below 5 degrees Celsius. 0 degrees Celsius is less than 5 degrees Celsius. -100. Sure hope that they don't keep keep the room that cold. That would be so cold. So our first step is to write the inequality, and we're going to let T represent the temperature in the lab. Before I do that, I want to write that the temperature is below 5 degrees Celsius. I need to figure out what inequality symbol I'm going to use to represent below. That's going to be a less than symbol because I selected numbers that were all less than 5. So the temperature is less than 5 degrees Celsius. But the problem asks us to use T to represent the temperature. So my inequality statement mathematically should be T is less than 5. And that represents that the temperature is less than 5 degrees Celsius. My next step is to graph the inequality. So my first action here is to draw, oh no, let me go back, is to draw make sure I have the right color. Draw a circle on 5, and because the symbol is less than, that's going to be an open circle. And I need to decide if I'm going to shade to the left or if I'm going to shade to the right. In this particular example, I selected numbers that were less than 5, like 0 and -4, and I think I said -100. That would be really, really chilly, -100 degrees Celsius. So I shaded all of the values that make this inequality true. And note that there's an arrow on the end of my number line here on the left. So that means it continues going, but that would be silly for me to draw a number line that went on forever. So my last step here is to check to make sure that I shaded in the right direction. So I'm going to pick a number in my shaded region. I'm going to pick -1, and I'm going to rewrite my inequality statement. T is less than 5, and I'm going to replace -1 in for T. I'm just checking, so I'm going to read -1 is less than 5. Well, that's true. So that means that I have the correct inequality statement and graph. Today, our objective was to define, write, and graph inequalities that represent real-world situations. Remember to refer back to the inequality table for information about the symbol, the type of circle on a number line, the meaning, and the word phrases that go with each symbol. This table is in your print packet. And now it's your turn to try some problems and show what you know. Look back at the examples in your print packet to help you. They are excellent models for you to refer to if you need some help. And now it's your turn to try some problems and show what you know. Look back at the examples in the print packet to help you. They are excellent models for you to refer to if you need some help. Let's re-energize our brain with another Think About It task. Today's Think About It task asks you to describe several different ways to go from Building 1 to South Street. Take a few seconds to think about 2 different ways you could use to go from Building 1 to South Street. Let's hear from my family to learn about their ideas. As you listen, think about how important good directions are when traveling. Hi, Spencer. Can you tell me how you would travel from Building 1 to South Street?
Yeah, so I'm at building 1. My car is parked here. I'd walk to my car. I'd make a right onto Thames Street, make a left onto Broadway. I'd make a right onto Cedar Street. I'd make a right onto Nassau Street.
Okay.
Then make a left onto Pine Street, and then I get to South Street.
So you took a pretty complicated route. Is there a reason why you didn't just follow the red line?
I was told not to follow the red line.
Ah, I see. Thanks, Spencer. All right, let's see what Finley has to say. How will you get from Building 1 to South Street?
I'll take a left on Broadway,
Okay.
a left on Thames Street, a left on Tiny Place, and then I'm going to turn left here,
Okay.
and then I'm going to turn left here, and then right here.
An exchange place?
Yes, and then
Okay.
keep going straight, and then turn right here, and then turn left here.
Onto Pearl Street?
Yeah, and then turn right here, and then I'm there.
Nice. Thanks, Sid. The The material covered in the second mini lesson is the same as the material in the print packet for Math 6 during the week of April 20th. This is lesson 2. On the screen is our second learning objective. Today we will find and position ordered pairs of integers and other rational numbers on the coordinate plane. Let's learn about it, the coordinate plane. You might remember from previous lessons or previous math courses some number lines. There's a horizontal number line, and you use it to plot rational numbers on this horizontal number line, but you also might remember a vertical number line. If we put both of the number lines on top of one another, it creates something called a coordinate plane. And we're going to take a look at the HMH Go Math player to explore some of the key features and the vocabulary of a coordinate plane.
A coordinate plane is formed by two number lines that intersect at right angles. The point of intersection is 0 on each number line. Which words will complete the sentences?
The two number lines are called the axes. The horizontal axis is called the x-axis, and I can see that it is labeled on the coordinate plane. The vertical axis is called the y-axis, and I can see that it is labeled on this coordinate plane. The point where the axes intersect is called the origin. This is this space here. The two number lines intersect at 0. And the two axes divide the coordinate plane into 4 quadrants. So let's see how we did. Nice. So now we're going to label the parts of the coordinate plane. So the two number lines are called the axes. And this looks like it's just information from what we filled in before. So it's pointing to the y-axis right here. So this is the y-axis. And this arrow is pointing to the x-axis. This is pointing to the intersection of the two number lines at 0, and that's called the origin. So we're going to label that. And the axes divide the coordinate plane into 4 quadrants. This is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. Let's see how we did.
Correct. The 4 sections are called quadrants. The number lines are axes. Where they meet is the origin. Now let's answer some questions about coordinates.
All right. An ordered pair is a pair of numbers that gives the location of a point on a coordinate plane. The first number tells us how far to the right, positive, or how far left, negative, the point is located from the origin. The second number tells us how far up or down the point is located from the origin. The first number in an ordered pair, the numbers in the ordered pair are called coordinates. And the first number is the x-coordinate and the second number is the y-coordinate.
Great. An ordered pair has an x-coordinate and a y-coordinate. These tell how far to move from the origin on the x-axis and the y-axis.
So now we're going to practice some of these types of questions. In this next Learn About It, we're going to complete an example where we're asked to identify the coordinates of point A and the coordinates of point B. So first, I'm going to take a look at point A, and I notice that that's located in quadrant 3. Remember, our quadrants are quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So I need directions to get from the origin to point A. So here are my directions. I'm going to start at the origin, and I'm going to move left 1 unit, and I'm going to move down 5 units. So I'm going to write an ordered pair that says -1, -5. Move left 5 and down 5. So that's what this looks like. Whoops, moved ahead. So oh my goodness. So my ordered pair is -1, -5. Those are the directions to get to point A from the origin. Now let's take a look at point B. Point B is located in quadrant 1. If I start at the origin, I need to move 2 units to the right and 3 units up. So my directions will be 2, 3. Remember, the coordinates of a point tell us how to move left or right, and that's going to be the first part, or the x coordinate, and then it tells us how to move up or down, and that's going to be the y coordinate. In the second example, we're asked to graph and label each point on the coordinate plane. I have 3 points, point A, point B, and point C. The first coordinate, or the first ordered pair, I'm going to do that in red, is -5, 2. So these directions are telling me that I'm going to move to the left 5 and up 2. So let's start at the origin and move to the left 5, 1, 2, 3, 4, 5, and up 2, 1, 2. Here is the point A, which is -5, 2. And that's located in quadrant 2. This is quadrant 2 right here. So for point B, I'll use green. So the directions for point B are telling me to move to the right 3 and up 1 5/10. So let's start at the origin and move to the right 3, 1, 2, 3, and up 1 5/10, 1 5/10. So point B is right here, 3, 1 5/10. And this is in quadrant 1. My last ordered pair is point C, and it's asking me to plot the point 0, -3. Let me move my video up. So these directions are saying 0. So I'm going to stay put, and I'm going to go down 3. So let's start at the origin, stay put, don't move left or right, and go down 3. 1, 2, 3. So this is point C, 0, -3. And this point is on the y-axis. In this last example, we're going to model a real-world situation. The graph shows the location of a city. So here's the city, and the city is at the origin. It also shows the location of Gary's house and Jen's house. The scale on each axis represents miles. Well, before I start with part A and, oh, that's a problem, okay. In this last Learn About It example, we're going to be modeling a real-world situation. The graph shows the location of a city. So here's the city, and the city looks like it's on the origin. It also shows the location of Gary's house and Jen's house. The scale on each axis, so here's the x-axis, and the y-axis represents miles. So one of the things that I'm noticing here is that the numbers on the x-axis and the y-axis aren't counting the same way as they were in the previous example. So it looks like the interval between each of the tick marks on the x and y axis is not 1, it's 5. So 5, 10, 15, 20. And if I look on the y-axis or the vertical number line, it's the same, 5, 10, 15, 20. So that's important for me to remember. Use the scale to describe Gary's location relative to the city. So what I'm going to do here is I'm going to actually represent Gary's house. Gary's house is blue with an ordered pair. So Gary's house is blue. I'm going to start at the origin and I need to go to the left, so I'll count 5, 10, 15, 20, 25. So I needed to go 25 miles to the left or west of the city, and I needed to go 5, 10, 15 miles north of the city. So I can do that in two ways. I can write that as an ordered pair, negative 25, 15, or I can say 25 miles west and 15 miles north. Oops. Jen's house is green. So we're going to start at the city, and we're going to go to Jen's house. So first we're going to travel east 5 miles, and then we're going to travel north 15 miles. So I can write this as an ordered pair, 5, 15, or I can say travel 5 miles east and 15 miles north. Today, our objective was to find and position ordered pairs of integers and other rational numbers on the coordinate plane. In your print packet, there is a graphic organizer that summarizes the vocabulary about the coordinate plane. There sure was a lot of vocabulary in this lesson. And now it's your turn to try some problems and show what you know. Look back at the examples in the print packet to give you some assistance. They're great models for you to refer to if you get stuck. Thanks so much for joining me today. I hope that you feel confident getting started on the problems in your print packet. Practicing what you learned is so important. Take care and stay well. See you soon.